Hey guys, in this video we're going to talk about extraneous solutions to logarithmic equations, and I'm going to show you how to do this algebraically and graphically. To solve these equations algebraically, we're going to apply properties of logarithms and algebraic properties of equality to solve for x. Our example on the left has two logs set equal to each other. With two equivalent logarithms, if the bases are the same, then so are the arguments. So we can write the equation 3x minus 5 equals x minus 11. We'll subtract x from both sides to collect all the variables on the left side of the equation, and add 5 to both sides to collect all the constants on the right side of the equation, which will leave us 2x equals negative 6. Now we divide both sides of the equation by 2 to isolate x, and we get x equals negative 3. Now we need to check our solution by substituting negative 3 back into the original equation in place of the x's. At first glance, it would seem that our solution is true because we have an equation that looks true, but we have to think about what this logarithmic expression really means. Remembering that a logarithm is just an exponent, we're going to ask ourselves, what exponent can we raise the base of 4 to get the argument value negative 14? And the answer is there isn't one, because there is no exponent that we can raise a positive base to get a negative outcome. So our solution of negative 3 is extraneous, therefore this equation has no solution. To solve the equation on the right, we're going to use the multiplication property of logarithms to condense the left-hand side of the equation down to one log. Since both of the logarithms are common logs, that means they're both base 10. And since they're the same base, we can rewrite them as a single log of the product of the individual arguments. Now we want to rewrite this logarithmic equation as an exponential equation of base 10 raised to the power of 2 equals the argument x squared minus 21x. Now we have a quadratic equation to solve. So I'm going to bring all the terms to the right-hand side of the equation, setting it equal to 0. And I'll solve it by factoring. And our factors of negative 100 that add up to negative 21 are negative 25 and positive 4, which give us the solutions 25 and negative 4. When we substitute these values back into the original equation in place of x, you should notice that once again we'll have a negative argument for one of those logs, and there is no exponent that we can raise a positive 10 to get a negative 4. So negative 4 is an extraneous solution, leaving us with the solution of 25. Remember that a solution is also known as a zero, a root, or an x-intercept. So to solve these graphically, we want to bring all the terms to one side of the equation, leaving a 0 on the other side. And then we'll use a graphing utility like the TI-Inspire or Desmos to graph our logarithmic expression as a function. So you should notice that our example on the left does not cross the x-axis, so it has no solution. And our example on the right only crosses the x-axis in one place. When we solved this equation algebraically, it generated two solutions, but we can see the graph of the function only crosses the x-axis once at 25, so the algebraic solution of negative 4 is extraneous. Let me know if you have any questions in the comment section below. Thanks for watching!